Hi guys, welcome. So in this video we'll learn how to calculate stress and strain in any plane or all the related analysis of stress strain when your load is applied in unidirection or in a single side. Let's say this is the body, you have applied load like this. Okay, so you have to calculate the stress, let's say in this plane or in this plane or in this plane, whatever may be the plane, you can calculate the stress. So let's see how you can calculate it. And remember, in exam like GATE or ESE, lots of questions are asked based on these fundamental things. Okay, so let's start. First, draw any body. Okay, let's say this one, and you are applying load here. Okay, so if the cross section is A, what is the stress in any particle plane like this? Simply stress sigma x, let's say this is the x direction, so stress sigma x is equal to your P by A. Okay, now rotate this plane anti-clockwise to reach this plane, and you have rotated this, let's say for 5 degree. Now I am asking you, what is the stress in this plane? Okay, simply again draw this for clarity. Okay, so this was your previous plane, now this is your current plane. Your applied load is acting like this. Okay, and this is phi. This area was A. So what is the area? This one, simply A by cos phi, simple geometry. Okay, and your load is here P. So stress, new stress, let's say S is load by area A dash, and new area is your A by cos phi. Clear? So your new stress is coming as P by A into cos phi, and or you can say P by A is your sigma x, this one. So S is your sigma x into cos phi. Okay, now if you draw this separately, let's draw it only the left side. Okay, so it looks like this, and your stress is acting like this. Let's say this is the S. Okay, so if I ask you what is the normal stress acting on this plane, you have to resolve this stress. This is the normal direction, and let denote this by sigma n. And what is the shear stress, or what is the stress parallel to this plane? Again you have to resolve this stress. If this is the angle phi, this angle is also phi, so to get sigma n, you have to resolve this S by its cos component, or S cos phi, and to get this shear stress or tau, you have to get the sine component, or S into sine phi. Clear? And you have already calculated the S, this one. So simply put this, sigma n is coming as your sigma x into cos phi multiplied with cos phi, or sigma x into cos square phi. Okay, so this is the normal stress acting on any plane which is 5 degree away from the original one. And what about this shear stress or tau? This is coming as S is your sigma x cos phi multiplied with sine phi. Okay, and if you can remember the formula, that for 2 sine phi into cos phi is equal to your sine 2 phi. Okay, you cannot, if you don't know this formula, you can check it. Okay, so you have got your normal stress, this one, and the shear stress, this one, for any plane. Okay, so whatever may be the whatever may be your plane here, this is your actual plane, and whatever may be the angle here. If you know this load and the original cross section, obviously you can find the normal stress as well as your shear stress in this new plane by applying these two formula. Okay, now this is the mathematical process to calculate this stress in any plane. There are also some graphical method, or there are some way you can actually plot the stress in graphical form, and then from that plotting you can find it easily. So let's see how we can plot this sigma n and your tau in graphical form. From these two equations you have already learned sigma n is equal to sigma x into cos square phi, and tau is equal to your sigma x by sine 2 phi. So what is the value of sigma n and tau for your value phi is equal to 0, or when your plane is here? Simply sigma n should come as your sigma x and tau is your 0. Okay, again, what about the stresses when your phi is 90 degree? Okay, or the plane parallel to this axis of the member, or parallel to the force. Okay, here phi is equal to pi by 2 or 90 degree. Let's say when your phi is equal to 90 degree, then sigma n is coming as cos phi for 90 degree is 0, so it is coming as 0, and also tau, as there is 2 phi, so sine 180 is 0, so tau is also your 0. Clear? Now take the sign convention first. Though it is quite simple, let me repeat for you. If it is tensile in nature, we take this normal stress as positive, and if this is compressive in nature, we take your normal stress as negative. And what about the shear stress? Consider any body and shear stress is acting like this. Here you can see this couple actually trying to rotate this element clockwise. That's why this is positive. And if this is acting anti-clockwise like this, here we will take this shear stress as negative. This is the sign convention. Okay, now let's represent these values graphically. Okay, so first take any orthogonal coordinate axis like this, and let's represent this x-axis by your normal stress, and this is for your shear stress. This is the positive direction, this is your positive direction, this is the negative direction, and this one is negative. Okay, clear? Now put first this value. Okay, for phi is equal to 0. Well, this is coming as your sigma x for normal stress, and for your shear stress there is no value, it is 0. Okay, again for phi is equal to 90 degree, this is your 0, so it is denoted by your origin. Okay, let's say this is A and this is your O or origin. Now if you draw any circle taking this or OA as diameter, take OA as your diameter and draw a circle. Okay, so it will something like this. It will look like this. The circle may not be perfect, I apologize for that. So this is the circle. Okay, now look here, you have taken the plane initially, this one here, phi is equal to 0, and for this condition the stress denoted is by point A. Okay, and when you have rotated this plane up to 90 degree and taken this plane, this the stresses in this plane is denoted by this point. So I can say that if I take this radius, okay, and rotate it by the angle twice of this one, I will get the point. This is my assumption, and this assumption will be proved if we can prove it for any angle phi. Okay, so if we can prove this, that for any angle phi, if we have to find the stresses in this plane, then we have to rotate this radius for angle 2 phi. Okay, and corresponding to that point, the normal stress and your shear stress should be matched with the formula which we have already find by mathematical computation. Okay, let's prove it. So again, clear a circle like this more clearly. Okay, so this is your axis and this is your sigma x or point A. Okay, and this is your origin. Now you have draw a circle like this. Let's say this is your circle, sorry for the shape. Okay, and take, this is the this is the radius or sigma x by 2. Now rotate this. This is the actual body where load has been applied, and we have to find stresses for this plane which is 5 degree away from the actual one. Okay, so our assumption was we have to rotate this radius counterclockwise for 2 phi. Okay, and then it is coming here. So what is the normal stress? The value of this one is also sigma x by 2. So the normal stress here is coming as your sigma n is equal to this one. Okay, first sigma x by 2 plus this portion. This is the cos component of sigma x by 2. Sigma x by 2 and its cos component. Sorry, this is cos 2 phi. Clear? If you simplify this, you will get that sigma x by 2 1 plus cos 2 phi, and 1 plus cos 2 phi means your 2 times of cos square phi. So cancelling 2 and 2, we are getting sigma x into cos square phi. What about the shear stress? Here the shear stress is denoted by this, or the sine component of this sigma x by 2. So tau is coming as sigma x by 2 and multiplied with sine 2 phi. So this is the value of sigma n and shear stress in this plane as per our graphical method with some assumption. So let's check these values with the mathematical computed value and prove whether, or check whether our assumption is correct or not. So for sigma n, it was sigma x multiplied with cos square phi. Here, yes, we have pass. And for tau, let's check. This is sigma x by 2 multiplied with sine 2 phi. Check. Yes, we have passed. So in this method you can find anywhere in this body, okay, what is the actual stress is. Let's say we are rotating this plane beyond pi by 2. When it has come here, this is pi by 2, and here this point is denoted by this one. Again we are rotating this plane, so the plane will be somewhere here like this when your phi is more than pi by 2. So simply we can calculate from this one graphical one. Let's calculate it. So we have to calculate this by rotating our radius here. This is for pi by 2 and this is for more than pi by 2. So here it will come somewhere here, and from that you can calculate. So this is your normal stress and this is your shear stress. Okay. Now let's say there is a situation when these two planes are mutually perpendicular. How? Okay. So let's say this is the body. Okay. This is the applied load P. This is the applied load P, and this was your actual axis. Now you have rotated first time. Let's say this is your PQ. You have rotated it for phi, and there is another plane which have been rotated by more than 90 degree somewhere here. Okay, let's say this is your MN. Okay, and the angle between these two is pi by 2, or these two planes are mutually perpendicular. Let's see what is the relation of the stresses which are acting on these two mutually perpendicular plane. Okay, so very first, again draw the circle. This is your circle. It is looks like this. Well, this time the circle looks quite better, and this was our A and this was O. Okay, and for PQ, okay, so for PQ, yes, now it's correct. For PQ we have rotated it. PQ means this one, so we have rotated it for 2 phi, and for MN we have to rotate it for how much? The angle between PQR, how much? Pi by 2. So to reach MN we have to rotate this more pi degree, because always we have to rotate in graphical system twice the required angle. Okay, so here this was for PQ, and now we have reached for MN. Okay, the angle between them are 180 degrees, so it is nothing but the diameter. So for PQ the stresses was, let's find them again. Sigma n was your sigma x into cos square your phi, something like that. Let's check it. Yes, it was that. And tau was sigma x by 2 multiplied with sine 2 phi. And here let's check what is the stress acting on MN, or this one. So for MN our point is coming here, and corresponding to this point the normal stress is only this much. What is this value? The sigma n dashed is equal to sigma x by 2 minus this value. This is the cos component of this one, or sigma x by 2, because this is the radius. So it is coming as sigma x by 2 into cos 2 phi. If we take common sigma x by 2, you will get 1 minus cos 2 phi. Again another formula, 1 minus cos 2 phi means your sigma x by 2 into, this means 2 times your sine square phi. Okay, cancel 2 and it is coming as sigma x into sine square phi. What about the shear stress? Tau dashed is equal to this one, this value, and we have already denoted this is the positive, this is the negative. So tau dashed is minus, the value is sine component of this one, or sigma x by 2 multiplied with sine 2 phi. Clear? So what is the relation between them? Let's check. If we add sigma n plus sigma n dash, normal stress in PQ and normal stress in Mn, it comes as sigma x cos square phi plus sigma x sine square phi. Sine square plus cos square theta is equal to 1, so it is coming as your sigma x. And what is the implication of this? That means any two mutually perpendicular plane, the summation of normal stress is constant. Okay, because this was your original stress. If you can remember, this was load P, this was P, this is the cross section A, and sigma x was P by A. Okay, and what about the shear stress? The shear stress tau dashed is minus this one, and this is nothing but tau. Okay, so minus of tau. Shear stress acting on Mn is negative of PQ. What is this implication? Well, it is a very good implication. Let's take, this is the shear stress, this is your shear stress acting in PQ, which is positive. Okay, so for Mn there must be a negative couple acting like this. Okay, sorry, this is negative because your relation says that. Okay, so take the plane again. Let's say this was your body and you applied load here. This was your PQ, and this is again, let's say, parallel to PQ, so stresses are same but PQ dashed, and this was your Mn, which is perpendicular to PQ, and again this is parallel to Mn. Let's denote with M test and N test. Now pick up this element, it looks like this, and for PQ you can see it is positive, so a positive couple is acting here, but in Mn it is negative, so it should act like this. Clear? So you can see here they are creating a resultant tensile force here and resultant compressive force here. So if this is a concrete material, you can say this concrete may be crushed due to this compressive load, and that's why in IS code there is a limitation of tau c max. Okay, this is the physics or the mechanics behind this tau c max. That's all. Again we will meet for another topic, maybe for soil mechanics or for solid mechanics or for any other subject related to your GATE and ESE. Till then, please practice from previous year with the aid of your textbook, and if you have any doubt related to this video or any type of problem, please let me know in the comment box.